Welcome to Unit 2, Forms of Matter, and we're going to be talking about gases. And we'll cover some of the basics. In your textbook, this is page 90 to 95, and we'll be talking about density, pressure, viscosity, moles, and molar mass. By the end of this lecture, you will be able to define qualities of matter such as density, pressure, viscosity, and mass. You'll be able to perform calculations based on density, and you'll be able to define the mole and molar mass. So density is defined as the mass of substance per unit volume. Generally, its base units will be grams per centimeter cubed or grams per milliliter. And just as an example, if you look at a cube of styrofoam, any size cube really of styrofoam compared to a similar sized cube of iron, the styrofoam will float on water, whereas the iron will not. What this means is the iron is more dense than the styrofoam, and it's actually more dense than the water as well, whereas the styrofoam is less dense than the water. Olive oil, another example would be, even liquids have density. Olive oil will float on water, while corn syrup will actually let water float on top of it. So what that would mean is olive oil is less dense than water, and water is less dense than corn syrup. So in terms of a formula, what the formula is, the density of an object is equal to the mass of that substance divided by the volume of that substance, or the weight of that substance, the amount of stuff you have, divided by the space that it takes up. In terms of formula, you'll see it as D is equal to M over V, or sometimes you'll also see it as rho. That little p is actually the Greek letter rho over mass, or is equal to mass divided by volume. And just an example of how one of these calculations would look. Osmium is the most dense element known, with a density of 22.5 grams per centimeter cubed. So I'm just going to write that down. We have a density equal to 22.5 grams per centimeter cubed. And we want to find the mass. So since it's asking me to find the mass, I'm just going to write down a little m with a question mark. Find the mass of a sample of osmium with a volume of 5 cubic centimeters. So now I also have a volume, and it's 5.0 centimeters cubed. And so now I have all the information from the question. I'm going to go through and see how I need to use my formula. So we know that density is equal to mass over volume. I want to find the mass. So what I'm going to do is I'm going to isolate mass by multiplying both sides by volume. When I do that, the volumes on the right side cancel out, and I'm left with volume times density is equal to mass. So if I multiply the volume times the density, I'll have the mass of my osmium sample. So I'm just going to go up over here. And I have the mass of osmium is equal to, and I have the volume first, so 5.0 cubic centimeters times 22.5 grams per cubic centimeter. Our cubic centimeters cancel, and when I multiply by two numbers together, I get 112.5 grams. Now I go back to my question, I take a look and see how many significant digits do I have. This number has 3. This number has 2. So I always go by the least, so I can only use 2 significant digits. So I'm going to change this into scientific notation. Move my decimal place 2 spots over. So my answer will be 1.1 times 10 squared grams. I'll just put a circle around my answer. So, pressure is another quantity that we're going to be measuring, and it's the force exerted on a surface divided by the area of that surface. In terms of units, the units are newtons, or forces measured in newtons, over square meters, which is equivalent to a Pascal. So a Newton per meter squared is equivalent to a Pascal. Generally speaking, we'll be using kilopascals. 1 kilopascal is equal to 1,000 pascals. For viscosity, Viscosity is the resistance to flow, and this is kind of like the thickness of a liquid or the thickness of a gas. And for example, water flows pretty easily. It has a low viscosity, while things like syrup and molasses do not flow very easily. They have very high viscosities. If you look at something like motor oil, it has a viscosity somewhere in between. It doesn't flow, it's not quite as thick as something like a molasses, but it's definitely thicker than a water. So it flows, it has a medium viscosity. Generally speaking, gases have very low viscosities. They flow very easily. And now we're going to look at the mole. And there's a couple of versions of what a mole might be, but not in chemistry. In chemistry, what the mole is it's a number, and it's a way of counting or grouping things together. A pair is 2. You can have a pair of shoes, which means you have 2 shoes. You can have a dozen objects, so a dozen is just shorthand for 12. And we can count dozens. A dozen donuts, 2 dozen donuts, 8 dozen donuts. It's easier to say 8 dozen donuts than it is to say 96 donuts, or have to actually count through 96 dozens, or 12 dozen donuts, which would be 144. But it's a way of counting without counting each individual object. So a century is another way of counting things. It's 100 objects. For example, 100 years would be a century. A gross is something that's a little bit less common. It's a group of 144 is called a gross. And I suppose you could have a gross of donuts. So the mole is the same idea. The mole is a number of objects. In chemistry, it's the number of atoms or the number of molecules in a sample. So 1 mole is equal to 6.02 times 10 to the 23rd objects. And for carbon, if you had 6.02 times 10 to the 23rd atoms of carbon, it would weigh 12.01 grams. This is also called the molar mass. The molar mass is the mass of 1 mole of substance. So we'll just make a note of that. Molar mass is the mass of 1 mole of a substance. And we use it for either atoms or molecules. So just to give you an idea about how many that is, in terms of chemistry, it would take 22.99 grams of sodium to have the 6.02 times 10 to the 23rd sodium atoms. The 6.02 is called Avogadro's number, or Avogadro's constant. It would be 18.02 grams of water would be the 6.02 times 10 to the 23rd water molecules. So that means that a water molecule actually weighs less than a sodium atom. A sodium atom must weigh a little bit more because 6.02 times 10 to the 23rd of them weighs a little more than 6.02 times 10 to the 23rd water molecules. We could say the same thing for another type of compound, aluminum hydroxide. In terms of size, 6.02 times 10 to the 23rd is an enormous number. And so we're just going to go through a couple of examples using the penny to show you how big that number is. If you were to count 5 pennies per second, and you wanted to count 1 mole of pennies, so you wanted to get up to that 6.02 times 10 to the 23rd, just counting 1, 2, 3, 4, 5, and so on, it would take you a really, really, really long time. If we just take a look at this number here, I'll just put my little commas in here. So we have here, this would be thousands, millions, billions, trillions, and so I believe this is quadrillions, but 38,000 trillion years to count that many pennies. So if you had a stack of pennies that contained 6.02 times 10 to the 23rd pennies, it would take you 3,800 trillion years. That's a really long time. That's longer than the Earth has been around. So, and in terms of doing the math, all I'm doing is a little unit analysis. I'm saying we have that many pennies, the 6.02 times 10 to the 23rd pennies. If we count in 1 second, if we can count 5 pennies, we're going to divide our number by 5. In 1 minute, there are 60 seconds, so seconds cancel with seconds. In 1 hour, there are 60 minutes, so our minutes cancel with minutes. In 1 day, there are 24 hours, so our hours cancel. And in 1 year, there are 365 days where this, I guess it would take you maybe a year less once you count in, or a couple of years less once you count in all those leap years that I ignored. But needless to say, to get units of years, we're going to divide our number by 5, by 60, by 60, by 24, and then by 365, and we still get a really, really huge number. If we were spending a mole of pennies, if you were able to spend $1 million or 100 million pennies every second, it would still take you 190 million years to spend $1 million every second if you had a mole of pennies. In order to transport your mole of pennies, it would take 3.9 times 10 to the 15 Liberty 282B dump trucks. It's the world's largest dump truck. To haul all of your pennies, you would need about 1 million of those, or 4 million of those, to transport. And here's the weight. This is the molar mass of a penny, but 1 mole of pennies weighs 1.41 kilograms, or 1.41 times 10 to the 21 kilograms. So again, it's a huge mass. You wouldn't be able to carry it around in your back pocket, that's for sure. So a mole is a huge number of things, but we have to use a mole because generally when we use the mole, we're counting atoms and molecules. And atoms and molecules are really, 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 really small things. So we have to count huge amounts of them in order to get units that we can comprehend in terms of everyday life. So we use the mole because we can't go by and count atoms one at a time. They're too small. So there's 2 ways you can count things, and an example would be when you go grocery shopping. You can buy things by count. For example, when you're buying a box of cereal, you're spending money per box. So $4.99 per box, $5.99 per box, and you would talk about how many boxes of cereal you bought. You wouldn't talk about how many. If you bought Cheerios, you wouldn't be talking about how many Cheerios you bought. You'd be talking about how many boxes of Cheerios you bought, because talking about the number of Cheerios you bought wouldn't make sense. You'd have to go into each box and count each Cheerio. The other way you can count or buy things is by mass. So when you buy fruit, for example, you're usually buying fruit by the kilogram or by the pound. And so they're not charging you per piece of fruit. They're charging you per mass of fruit you buy. And so we use moles in the same way. Generally speaking, we know the mass of something because we can weigh that easily. We can put it on a scale, find out its mass, and then what we need to do is we need to convert it to moles, because molecules react on a molecular level or on a piece-by-piece level. They don't react on a mass level, or they don't have easy to find mass ratios. So the atomic mass on your periodic table is the mass of 1 mole of atoms of an element. It's the number that's in the top right-hand side of each of those elemental symbols. And if you take a look at just the copper symbol on your periodic table, in the top right-hand corner it says that there's a 63.55 grams. And so what this means is that if you were able to count out 6.02 times 10 to the 23rd copper atoms, you would have a mass that equals 63.55 grams on a scale. Or if you put onto a scale 63.55 grams exactly of pure copper, you would have 1 mole of copper atoms, or 6.02 times 10 to the 23rd atoms. So this is called molar mass. And one of the reasons we use moles is because when chemicals react with each other, they react with each other on an atom per atom basis. So this equation can be read as 1 atom of zinc reacts with 2 molecules of hydrochloric acid to produce 1 molecule of zinc chloride and 1 molecule of elemental hydrogen. By the same token, we could count it by dozens. We could say there's a dozen atoms of zinc reacting with 2 dozens of hydrochloric acid to produce 1 dozen molecules of zinc chloride and 1 dozen molecules of elemental hydrogen. The mole works the same way. The first statement is counting atom by atom. The second would be counting by dozens of atoms, but for atoms, even a dozen is too small to count. We can't see a dozen atoms when they're stacked together. You need an electron microscope to see something that small, which most of us don't have. So the mole works the same way. instead of counting things by dozens, we count them by moles, because we can see 1 mole of zinc. So a mole of zinc reacts with 2 moles of aqueous hydrochloric acid to produce 1 mole of aqueous zinc chloride and 1 mole of elemental hydrogen. So the reason we use the mole is because we can't measure moles directly. We can't actually count out the atoms. It would take too long and they're too small. So we weigh them out and then find out the number of moles by the mass that we actually have. So for our next lecture, we're going to be looking at the mass of a sample and the mass, and we're going to relate the mass of a sample of matter to the number of particles in that sample, or the number of atoms or molecules, and we're going to measure it in moles. So in terms of homework, try out the practice problems on page, that's the wrong page, hold on a second. So on page 95, questions 1 to 4. Once you're done those, go on and read Appendix D in your textbook. It's about significant digits in scientific notation. There's 3 pages on it, just on how you're going to communicate numbers, how to do things in scientific notation, the practice problems. There's 2 sets. There's 1 on page 771, and there's 2 on page 772.